simple definition in terms of physics, resonance can be defined as a phenomenon in which a vibrating system or an external force drives another system to oscillate with a greater amplitude at a specific frequency. We are going to use the same concept for our circuits in network theory. So one simple example of resonance is how the pendulum vibrates. So at a particular frequency, it will start gaining a greater amplitude and start swinging fast. Now we are dealing with network theory wherein we make use of AC circuits. Now these AC circuits use the AC source with the network elements. The network elements could be the resistance, inductance, or the capacitor. If we are going to have the inductor and capacitor, these are the energy elements in this circuit. So based on the number of energy elements that you have in this circuit, we can classify them as first order circuit, second order circuit, or a third order circuit. So first order circuit is one where you have one energy element. It could be either an inductor or a capacitor. Only single energy element is present. Second order circuits are where you have two energy elements. So in this case, you can have two inductors, two capacitors, or one inductor and one capacitor. Third order circuits are the ones where you have three energy elements. Again, in this case, we can have two capacitors and one inductor, or one capacitor and two inductors. So the combination can be different, but mainly the number of energy elements are important. Now let us define what is a resonance circuit. So any AC circuit can be called as a resonance circuit under the condition that the current drawn from the supply is in phase with the sinusoidal voltage. So graphically, I can represent this as a waveform corresponding to the voltage, that is the applied voltage. Let me name this as V. This is the voltage with respect to time, and this is the waveform corresponding to the current. We name this as I. So if you see, the waveform for current is in phase with the applied voltage. So when it is in phase with this applied voltage, we say the circuit is behaving like a resonance circuit. So the next question that comes to our mind is to how to achieve this resonance. How to achieve resonance or the resonance condition. So to achieve resonance, we have two ways. The first thing that you can do is either keep the network elements constant and vary the frequency, because you know we are dealing with AC circuits, right? So this is dependent on frequency. So keep either the network elements constant and vary the frequency, or keep the frequency constant and vary the network elements or the circuit elements. Okay, so to achieve resonance, you can do it either way. So as per the definition, let us look into the three properties that need to be satisfied by a resonance circuit. The first one is that the resultant reactance. When I say the resultant reactance, it means if you are using the inductor, the reactance will be XL, and if you are using the capacitor, it will be XC. Okay, the resultant reactance or susceptance. Susceptance is basically the inverse of reactance. Okay, the susceptance should be equal to 0. So to compute susceptance, when I say inverse, for an inductor, BL will be equal to 1 by XL, and for capacitor it is BC equal to 1 by XC. So the resultant reactance, the number of network elements that are present in the circuit, including all of them, the resultant reactance or susceptance should be equal to 0. The second property is that the circuit should be or behave as a resistive circuit. That means it should be pure resistance. And this condition is achieved if XL is equal to XC. So at resonance, the inductive reactance will be equal to the capacitive reactance. So remember this property. I will explain you in much detail when we find out using the derivation how the network is a pure resistive network or a pure resistive circuit. Okay. Then the third property is that the power factor is unity. That is because power factor is computed as cos phi, and since there is no phase shift, phi is equal to 0, therefore cos phi will be equal to 1. Let us look into some of the applications or use of resonance in everyday life. Radio, TV. Okay, the simplest one which I told you earlier, pendulum, guitar. Even when you sing very loudly, if there are glasses or if you play your music very loud at one particular frequency, when it is reached, what happens is that your glass will break. So we can apply it to the radio and so on. So there are n number of applications. So let me see just or consider how it is very much applicable in the case of a radio. So in the radio, what happens is that you have a circuit, you are having a knob, you're varying that knob, that means you're basically varying your input voltage, and this circuit consists of the various components, say RLC. So the output of this particular circuit will respond at every frequency. If you see, when you use your radios, until you adjust it to a particular frequency, it'll start making some noise, correct? So it is at one particular frequency that you will get your tuned radio signal. So say for example, if you are listening to 98.3 FM, okay, so before you reach 98.3 or after you reach 98.3, after means if you're turning your knob still more, there will be interference or the noise. It is only at the frequency 98.3 you will get the signal. So I can say, if I plot this in terms of a response, if this is a graph of frequency versus the current, then I can say that at the frequency ft equal to 98.3, that is the current is maximum, and I able to hear this particular frequency signal. But if you want to reduce the noise, as I said, before 98.3 and after 98.3 also you can hear some interference. So if you want to reduce the interference, this particular band, okay, this particular band should be narrower. So if it is narrower and narrower, the interference will be minimum. If not, you can see that somewhere close to 92.5 FM also you will be getting some signal. Okay, so you should see to it that this band is very, very narrow. Coming to other applications, you can apply this concept of resonance in tuned circuits, which also are used in your FM, in filter circuits, signal processing, and control engineering, and so on. We did look into what is a resonance circuit, right? Now coming to the classification of resonance circuits. Resonance circuits can be of two types: series resonance circuit, or you can have a parallel resonance circuit. Series resonance circuit is when you have the network elements R, L and C connected in series. Parallel resonance circuit is where you have the components R, L, C connected in parallel. The basic functionalities that you should be knowing before we get into these concepts. If you look at the inductor, the reactance is given by XL to be equal to 2 pi FL, right? So this can be represented as omega L, and the representation in terms of impedance will be J omega L, okay? Or I can also write this as JXL, since omega is equal to 2 pi f. Omega corresponds to the angular frequency. So omega is equal to 2 pi f. So I can represent the impedance either as j omega L or j XL. Then you have the capacitor, wherein the reactance is given by 1 by 2 pi f c. I can write this as 1 by omega c. And the impedance can be written as minus j by omega c or 1 by j omega c. And I can write this in terms of the reactance as minus jxc. Now when we are considering the circuit, whether the series resonance or the parallel resonance, we will be representing in terms of the impedance, that is the parameter Z. So this impedance Z in terms of the Ohm's law can be given as equal to V by I. So this is the AC notation or the phasor notation, and it's a complex number basically. When I say AC or phasor notation, this impedance Z gives you the phase shift between the current and voltage. Say I'm considering a series circuit, okay? So I will have a resistance R, I will have an inductance L and a capacitance C. So if I'm supposed to compute the total impedance of this circuit, I can write this as R. This will be represented as JXL. This is minus JXC. So I can write this as R plus JXL minus JXC, or I can write this as, taking the J common, R plus JXL minus XC. See, this is the total impedance of the circuit, okay, for a series circuit if I am considering in this case. Okay, we'll see how this equation is obtained in the series resonance circuit, but for your understanding I am saying here this is the total impedance that you have. Okay, now the value of this complex number Z, that is your impedance, can be a positive or a negative value. Okay, so when you have Z to be positive, the voltage will lead the current, and when Z is negative, voltage will lag the current. That is because if you look at this particular impedance equation, this is equal to saying R plus JX if I am considering X to be equal to XL minus XC. That is because if you see here, this is an inductor. In an inductor, the voltage will lead the current, whereas in a capacitor, the voltage will lag the current. So the same thing applies for the equation for impedance. If Z is positive, that means your XL, your capacitive reactance, XL is greater and the value of Z will be positive. So your inductive reactance will be acting very highly. So voltage will lead the current. Whereas if your capacitive reactance is higher, Z will be negative and the voltage will lag the current.